Okay, welcome everybody. So this next chapter that we're going to talk about is called Redox, Oxidation Reduction Chemistry. We put the two words together and we have reduction, oxidation, or redox. So we need to make some definitions about each of these terms, oxidation, reduction. Something important that you need to know is that oxidation, reduction, it happens simultaneously. So oxidation and reduction, it is like good and evil, and they go together. You can't just have an oxidation occurring without a reduction occurring. You can't have a reduction without an oxidation. So what are some of the definitions here? Well, a reduction, it is defined as the gain of electrons. So if you gain electrons, you would undergo reduction. So you might be thinking, well, why do they call it a reduction if you're gaining something? Well, what's actually happening is you gain the electrons, you reduce the charge. And so, for example, if I were to have something like, platinum plus 2, if it were to gain electrons, then it would become platinum. Notice a couple of important things here. The platinum gained 2 electrons, they're on the left side, and it forms platinum metal. The charge went from plus 2 down to 0. Now, what is an oxidation? An oxidation is a loss of electrons. And this would be where the charge gets higher. The charge increases. So what does this look like with a charge increasing? Well, let's say that we were to have something like aluminum, and the aluminum were to become plus 3. Well, how does it become plus 3? Well, it would gain 3 electrons. It would lose 3 electrons. And you see those electrons coming out as a product being lost. Now, where does this term oxidation come from? You might be thinking, well, it should involve some kind of oxygen. Oxidation happens in oxygen. And the reason why we call it oxidation, colloquially speaking, is because, in fact, most oxidation reactions occur in or traditionally involved oxygen. Oxygen, if you remember, if you look at the periodic table, it's all the way on the right side of the periodic table. And in fact, it is a very good, what's known as oxidizing agent. It is something that will easily remove electrons from other elements. We see this with rusting. We see this with combustion. Oxygen is very good at removing electrons and at oxidizing things, at adding oxygen to them. So something to think about is in biology and other sciences, people use alternate definitions for this. A reduction in biology a lot of times will be the addition of hydrogen. And oxidation will be exactly like it sounds, the addition of oxygen. In chemistry and for the Regents and the SAT, they generally stick to the electron definition though. So how do we know when a redox reaction actually occurs? Well, first of all, one thing that's really important to know is that all synthesis, complete decompositions, single replacements, and combustion reactions are redox reactions. They involve some kind of transfer of electrons. So they have a transfer of electrons. But all of these reactions have something in common with each other. And what they have in common with each other is that they have uncombined neutral elements. So elements that are uncombined, like sodium and chlorine and sulfur, even though there's 2 chlorines and 8 sulfurs, all of those elements are uncombined neutral elements, and if you see them in a reaction, then you know that, in fact, the reaction is probably undergoing an oxidation reduction. Now, if you want a surefire way to say, well, what if I come up with this sort of like exception where that doesn't work? If you want a surefire way to actually figure out is a reduction oxidation reaction occurring, assign oxidation numbers. See that the oxidation numbers are changing. And you might be thinking to yourself, okay, well, how do I know what a oxidation number is. How do I actually figure that out? And so that's what we're going to do right now. We're going to assign oxidation numbers so that you'll know what they are. Now, depending on where you read or where you look at, there are different rules and different sets of rules. I've seen up to 10 different rules. And honestly, I try to pare back on the rules. I don't need you to memorize a whole list of oxidation assigning rules. I sort of pared it down to the most important ones. Oxidation numbers, what they tell us is what the charge of the element would be in a compound if it was ionic. If the compound was ionic, what would the charge be? So the first rule that you need to know is that elements that are by themselves, that are not part of a compound, have an oxidation number of 0. Again, that includes any of the diatomics or any of the weird ones that have like 8 elements, like S8, P4, Cl2, C60, any of these elements, they all have an oxidation number of 0. Now, we can use the periodic table to assign oxidation numbers to elements. And what do I mean by that? Well, if you're in group 1, then you're +1. If you're in group 2, then you're +2. If you're in group 13, you're +3. Now, things get a little bit weird when you get to group 14. When you're in group 14, you actually have a range. You can range from +4 all the way to -4, and we'll do examples where you'll see that. If you're in group 15, you can range from +5 all the way to -3. If you're in group 16, you could range from +6 all the way to -2. And if you're in group 17, then you could range from +7 to -1. So those are the ranges that can be. Now, the thing with this is that in group 16, the most common element that we deal with is oxygen. Oxygen does not range from +6 to -2. Oxygen has a much smaller range. And so when you look at this and you're like, well, what would the range be for oxygen? Oxygen is almost always -2. Oxygen is almost always negative. So oxygen will have an oxidation number of almost always -2. Now there are a few exceptions for oxygen that, will have it not be -2. One of those is when you have oxygen in a peroxide. So when we have oxygen as a peroxide, it's really O2 -2. And in that case, since there's 2 oxygens that are together -2, oxygen will be -1. So the other exception that is important for you to know about is with hydrogen. Hydrogen is almost always +1. But there are cases where you put it with a metal like KH. And in this case, hydrogen will be -1. They call this a hydride. If you're unsure about which one should get the more negative charge, look at their electronegativities. The element that is more electronegative will certainly get the more negative oxidation number. Now, the other rules are you should assign oxidation numbers to elements that only have one or one sure one first. Then, if the element has more than one oxidation number, you need to go through and choose the right one. The right one that you choose is going to be one that's going to cancel out the other charges and make the compound neutral. So let me show you an example here, KMnO4, right? So K, if I look at K on the periodic table, it's in group 1. So since K is in group 1, it's going to be +1. This is the oxidation number. There's number of atoms here. K is 1 atom. So the total charge for K in this compound is +1 times 1, so it's +1. Mn, if you look at the periodic table, it's a transition element. It has more than one charge. We're going to go back to that one. Oxygen, it's not in a peroxide, so its charge is -2. So oxygen is -2. There are 4 of them, so if we multiply them together, we get a total charge of -8. Now, the Mn has to be something to cancel out that total charge. We have +1, we have -8, that makes -7, so Mn would have to be +7. There's only one Mn, so Mn's charge is +7. This oxidation number of Mn is what I'm looking for. I'm not interested in the total charge, I'm interested in the charge of each individual element. If you want to do it on the side here to show you, I could zoom in here as a shortcut. K is +1 and there's 1 of them, so it's +1. O is -2 and there's 4 of them, so it's -8. They have to add up to 0 to make it neutral, so they would add up to 0. Mn would be +7 to balance it out. Now, let's look down here at Na2Cr2O7. So in this case, Na is +1, and there's 2 of them, so its total is +2. Cr is a transition element again, we don't know exactly what it is. O is not a peroxide, it's -2. There's 7 of them, so it's -14. We need the difference between them. In this case, the difference is going to be -12, and so the Cr will be +12, but there's 2 of them. So what charge times 2 would give me +2? It's +6. Again, we could take the shortcut over here. +1 times 2 is +2. -2 times 7 is -14. They have to add up to 0. So the difference between them, that would make this equal to 12. And there's 2 CRs, so it's +6. What if we have an ion down here? If I have an ion, instead of them being equal to 0, they're going to be equal to -1. So in this case, I have Cl. I don't know. It could have multiple charges. It's in group 17. It could be anywhere from -1 to +7. O, though, is pretty much always -2. It's not in a peroxide. There's 3 O's, so it's -6. Again, we want the total to be equal to -1 now. So Cl would be +5 to balance that out. There's 1 of them, so each Cl has an oxidation number of +5. If you want to do the shortcut, you could do equals -1. So this would be -2 times 3 is -6 for oxygen. This would be +5 then. Since there's 1 Cl, everyone is +5. So as you can see, here are some that you can do. Let's practice some, and I'll give you some that you can practice some, bring in tomorrow. Let's try something like H2O2. Let's try something like C2O4. Let's try something like CuNO32. Let's try something like KClO2. And then let's try something like SNO2. All right, good luck. Try those 5. Thanks for watching.